So welcome back to the afternoon session. Our next talk in here is from a platinum sponsor, Synopsys. Our speaker is Iain Singleton, who's an applications engineer. The title of the talk is Fault Injection and Formal, Made for Each Other. Iain is a formal verification specialist in the verification group at Synopsys. Prior to Synopsys, Iain worked in the advanced verification methodology group at Imagination Technologies as a formal engineer tasked with solving tough formal problems, as opposed to easy ones, tough formal problems across the company. He holds a master's degree in electronic engineering from Newcastle University. Over to him.
Thanks very much, Mike. Okay, afternoon, everybody. Yeah, thank you for that introduction, Mike. My name's Iain Singleton, and I've been tasked with keeping you all awake after lunch, which is never an easy task, so I thought I'd start with a nice lullaby of fault injection and formal, the love story of the two of them, and how really they are made for each other. But I know you're all really excited to hear about formal anyway, so hopefully the talk will be interesting and you're all read up and ready to go. So, as you can see from my Pixar level animation skills over here, formal usage has grown hugely in the past few years. This is something which I don't think now there's anyone who can deny. When we go back several years, formal was kind of confined a little bit, kind of to the metaphorical basements of companies where you had these kind of weird guys with their PhDs who don't want to talk to anyone, who hide away and they do a little bit of formal. And there's not really any kind of structure to it as such. There's not really any kind of how we actually apply this or strategy for how we move forward. But usage has grown hugely in recent years. And you'll actually struggle nowadays to find yourself companies working in the semiconductor IP industry where they're not using some kind of formal. So a few months ago at a DAC in the US, Synopsys held a panel discussion where we actually said, should we be going deep with formal or should we be going broad with formal? The idea of, do we go deep into the design space with full exhaustive proofs and full formal sign-off? Or do we apply this more at the app-based level where we allow designers to apply formal, people with less experience to do it? And the summary from the talk was that actually both of these approaches are right. And across the board, we're seeing people from design engineers all the way through to full formal sign-off adopting formal. Now, this isn't necessarily as good as it could be today. There's definitely improvements that can be made, and there's definitely more formal that we can do. But it's come a long way. As a result of that, though, we've developed lots of new metrics. As formal's grown in the industry, and as more companies have started to adopt it, people have started saying to themselves, well, how can I actually integrate this into my verification flow? How do I actually start measuring something about this? How can I actually say, rather than just trusting somebody to tell me I've proven this about your design, how do I actually take a measurement and say, I feel confident that this design has been verified. I feel confident that I've checked this particular part of logic. So the question becomes, with all of these new metrics that have been introduced, and there have been various different ones that will have been thrown at you from different EDA vendors and different people, which ones should we be using and which ones should we be using them for? So that's what I want to try and go through in this talk today and try and discuss with you the different metrics we have, why they're useful, and then lead into fault injection. So the first one of these that you might hear people talk about is this idea of cone of influence based. This idea that we can do something with a cone of influence to measure our formal environment. Cone of influence based verification analysis is the simplest kind of metric we can measure using formal. You may hear it given different names from different vendors or things, but essentially all we're trying to do is say, if I have a set of properties that sit within my state space, I have logic that sits within this state space, and I can form a cone of influence of logic that leads all the way back to the primary inputs that tells me which pieces of logic sit within the influencing cone of my assertions. If I can tell you that there is logic sitting inside these cones, it doesn't really mean anything. But if I can tell you that there's logic that sits outside of those cones of influence, it actually means a great deal. Cone of influence analysis is quick and easy to run. It's a structural analysis that doesn't take any time. We just can generate you a report nice and easy. And it'll identify holes in the verification. Just because something sits within a cone of influence, I can't be confident about how that's been checked. But if something sits outside of the cone of influence, I can tell you for sure that there's no assertion within my formal environment that's testing this piece of logic. So it's a really good negative indicator, but it doesn't prove anything inside of the cone of influence. So it's great for a first pass sanity check, but we can't really sign off on formal using just cone of influence analysis. We can tell you what you've missed. Then you go fix that, you go add more assertions, you go change your assertions, and then you run this again, but only when you actually got this at 100% should we really be looking at moving forward. So what else do we have? Something else we look at is overconstraint analysis. So overconstraint analysis is really important to do because it's very difficult to tell if you have an overconstraint in formal. If I have an underconstraint, it'll be blindingly obvious to me because I'll have generated myself a lovely counterexample that makes no sense. I'll take it to a designer and he'll say, why on earth are you giving me this scenario? This will never happen. And this is kind of the pain that formal engineers sometimes have of building the correct constraints. Under constraints, very easy. We see those false failures. Over constraints, a little bit harder. What happens if I prove something and I've said, well, formal's great, formal's exhaustive, I've proven something about this. But if I've proven it in an over-constrained environment, I'll just see that proof and I won't know that it was proven in a way that actually wasn't allowing all possible behaviors to happen. So what can we do in terms of actually analyzing the state space and figuring out if we have over-constraints? Well, we can take a look at the design and use formal technology to identify unreachable logic in the design without any constraints, and then unreachable logic within the design because of constraints. Without any constraints in the design, anything that the tool proves me is unreachable is dead code. It just can't be reached in the design. With constraints, however, the difference between these two is logic which is unreachable because of constraints that I added. You can actually tell whether or not an over-constraint is present in your design by identifying whether you're stopping certain pieces of logic being hit as a result of those constraints. So over-constraint analysis is going to identify unreachable code. It's really nice and easy to run. There's no kind of hardship in running this. It's going to determine if my proofs are genuine. It's going to tell me if my proofs are any good, but it's not going to tell me what's actually being checked. So while cone of influence analysis was a lovely first pass analysis telling us about our assertions and if we'd missed anything, over-constraint analysis is now actually telling us, are my proofs any good? Have I over-constrained anything? So it's an important part of the sign-off flow. Again, we can't really sign off on this. All it's doing is telling me if my proofs are any good. It doesn't mean that I've checked everything about my design. So we need to go back again and look at what more we can do. The next thing we look at is when we start to actually come into more detailed analysis or more accurate measurements of what your formal environment has tested about your design. So here we have this idea of a formal core. Formal core, again, may be called different things depending on who's telling you about it. But essentially, it's a formal analysis that gets done based on the assertions that you wrote, and it will tell you which pieces of logic are actually involved in the results of your assertion. So the formal core is generally a subset of the cone of influence. Your cone of influence is just a structural analysis. What logic is actually sitting in my design space? What logic feeds into this assertion? Formal core brings in the concept of formal engines, performing a formal analysis, and telling you which of these pieces of logic actually affect the result of an assertion. Now, this is really cool because formal is an exhaustive thing in and of itself. So if we can now perform an analysis to tell you which pieces of logic are actually affecting this, you can start to get a good idea of really what you've tested about your design. It's a lot more than you'd get from some coverage metrics from other verification methodologies, and it will tell you a lot of interesting things. So formal core is reporting for me what's been checked by formal. It's a much more accurate metric than a cone of influence. Unfortunately, there's a bigger overhead for it because it's a formal analysis. So that's why we recommend running like a cone of influence analysis first, because that'll just give you some structural results. Formal core has to run a formal analysis, but it will give you more accurate results. It'll identify holes in the verification for you, and it'll report logic that's truly involved in a given proof. So this is good. This is a robust metric. Some companies do use it to sign off with formal. Some companies are using formal core-based analysis to actually take their designs and sign off on them and say, okay, I'm happy with what I've tested here. However, it doesn't answer all of the questions. Just because I've told you that I've tested a piece of logic, that doesn't mean I've tested everything about it. Yeah, okay, my 64-bit counter might be involved in some sort of proof, but it doesn't mean I've proven everything about that. There could be a really serious bug in there. So although formal core tells me what I've checked, it doesn't tell me that I've checked everything about that. So we need to go one step further. If we want this really accurate thing that we get from formal, we need to go one step further. So this is when we move on to the idea of fault injection. Now, fault injection is nothing new. This isn't a new concept, and you see this across different types of verification. It's been around for a while. But the idea with fault injection is that I can inject some faults into the RTL. I can take the design, and I can inject these bugs into the design. And now I want to check that my verification environment is actually able to catch these faults, these issues that I've inserted in there. If I am able to catch all of the issues that I've inserted into my design, then that can give me a relatively good confidence to say, I feel like my verification environment is good. I feel like I'm testing everything because I can catch all of these bugs. So it's the highest level of verification we can do in terms of this pyramid that I've been talking about today, from cone of influence through overconstraint, formal core, and now to actually fault injection. In a formal context, and I'll go into this in more detail, what we want to say is if no assertion fails, that should be a red flag. So in my formal environment, if I run my assertions with an injected fault and none of them fail, that's a problem. I seem to have missed something. So this is what we actually then use at the top of the tree for a formal sign-off. And fault injection, mutation-based analysis, whether or not it's automated by a tool or whether it's something which is done manually, is one of the highest forms of verification that we can do. So in a nutshell, what we do when we try and use fault injection is we take the design, automatically insert some artificial bugs into the design, these faults in there, run the verification process on this broken design, and measure the ability of this environment to do three things: activate, propagate, detect the faults. That's kind of the summary of what we're trying to do with fault injection. And this is applicable across different verification domains. So I'm going to go into this into the context of formal, but fault injection is just as applicable in the simulation context. You can insert faults into designs for simulation and ensure that you've caught those faults. You're testing your testing environment, and this is an important thing for you to be able to do. When we actually look at it with formal, how are we doing things? What are we actually modifying about the design? What sort of things do we want to change in there, and how can we do this easily? So we might want to, for example, time certain pieces of logic to constant values. We might want to try and test forcing the execution of particular branches. So I might want to try and force the execution of an if branch and an if else. I might want to try changing some logical operators. We then want to take this broken design, pass it on to formal verification, and then say, if at least one of my assertions fails, that's good. I caught this bug I inserted. However, if all my assertions pass, then that's a problem. So this is when you start asking the question, how is this possible? How is it scalable to do all this? If you imagine the idea that I have to go and actually say, tie this to constant, run all my assertions, does one of them fail? Yes. Okay, go back now. Let's try forcing this if branch. Run all my assertions. Do any of them fail? And you have to do this iteratively over and over and over again. It's not a scalable process to be able to do everything manually. There's benefit to manual fault injection, but wouldn't it be great if there was a way that we could actually try and automate this through the use of some kind of tool or try and make it easier? So this is when I come to the synopsis-y part of the presentation, because I hope you didn't think you were getting away that easily. This is our app space that we have with VC Formal today, which kind of shows you a bunch of different apps for various verification technologies. I'm not going to go into them because they're not part of this talk, but if there's any interesting things, we can talk in more details offline. The one I want to focus on is this guy down in the corner here, which is the formal Testbench analyzer. Now, the formal Testbench analyzer takes this concept that I've been talking to you about, this concept of injecting faults in the design, checking whether or not my assertions can catch them, and actually creates an automated environment to run that for you and make it much easier for you to see whether or not you can catch injected faults in the RTL. So formal Testbench analyzer is going to take RTL, and it's going to use one of our tools which we've integrated into VC Formal called Certitude, that some of you may be aware of. It's going to take Certitude, and Certitude will instrument faults into the model. It will inject a whole bunch of faults in there that are under different activation conditions, different if-def conditions, and it will then bring that up in the tool. And you can switch this on from day zero. You know, when you're bringing up your design for FPV, when you're doing your verification, you can switch on the fault model. And that means that when you're ready, once you've finished your verification, once you've looked at all your assertions, once you've made sure everything's passed, you're ready within the tool to just say, okay, drop me into FTA. When I drop you into FTA, I'm going to have all these faults that are nicely inserted for you, each of them individually asserted, and then I can run the assertions, and the tool will then come back to me with the results and tell me whether or not I was able to catch bugs with these assertions. So one of the other questions that might be asked is actual performance considerations. So I've mentioned automatically instrumenting the faults. This makes our lives easier. You know, you don't have to go and individually tie this to zero, force this, change this logical operator. We can automate that for you. However, performance may also be a consideration. When we talk about model checking, we look at the scalability of things. Imagine if I've got 100 assertions, and it takes some time for me to be able to prove all these assertions. That can cause performance impact. If I've got hundreds and hundreds of faults to inject here, again, how do I actually turn that into a scalable solution to make it easier? We've automatically injected these faults for you. But there's actually a lot of things that we can do in terms of performance as well. So one of the ways we can optimize the runtime is this native integration of certitude into the FTA app. The actual way we've integrated this and the way we've optimized it for Formal means that we actually see around about a 5x improvement in runtime versus running certitude with a standalone Formal tool. That's a big deal, and it's actually proven to be very useful for people. We can also do pruning of the cone of influence. So what do I mean when I say that? Well, if I inject a fault into the design, is there any point in me running all of the assertions if I can tell you structurally that this fault isn't going to affect the result of 80% of them? And the answer to that question is obviously no. So rather than running these assertions that I know it won't affect the result of, because I perform my structural cone of influence analysis under the hood, I can hugely reduce the number of assertions that I actually need to run for any given fault. We can also then use native server farm support to actually throw all this out onto an LSF. So then you can have all of these faults which have been instrumented being run with a very minimal set of assertions, and you get a much faster turnaround time than you would have if you'd have done this any other way. It's also important to note that when we've been talking about this, I went through kind of stages of Formal sign-off. I went through stages of running cone of influence, looking at our overconstraints. Then we looked at a Formal core, and then we came to the top of the tree, which is where we were starting to look at FTA and inserting faults in the design. Because we're at this stage, it means that using other metrics should have covered a lot of the holes in the verification. And because of that, it means that you're expecting your assertions to fail as a result of these faults. You're not expecting to find loads and loads of holes in your verification. And generally speaking, we can find you a counterexample with Formal a lot quicker than we can find you a proof. And so if we're actually expecting counterexamples because we've done the due diligence up to this point of making sure that we don't have any obvious holes in there, then our runtime gets dramatically reduced and we can catch these failures easily. So because we've explored all of this, because we've done all of the different steps to get to this stage, it's a lot easier for us to run our FTA app. So this then becomes a match that's made in heaven or mountain view, and depending on your view of the valley, you can decide whether that really is heaven or hell. Formal is exhaustive. So because Formal is exhaustive, it means that we're testing all possibilities. That's the thing that all of us who've looked for Formal have been waving our flags at management for ages now, saying, I can test all your scenarios. I can make sure that I've tested everything for you. All we need to do, though, is actually make sure we're asking the right questions. Yes, I'll tell you whether or not the answer to your question is everything works all the time, but have you asked the right question? Any bug that can't be caught indicates that we aren't asking the right questions. It indicates that our assertions need changing. It indicates that maybe we need to add more assertions. So actually using fault injection is helping us to test that final thing that needs asking about Formal is, did we ask the right question? Because Formal will tell us whether or not the result of that question was correct. VC Formal FTA is actually optimizing the number of faults without any loss of efficiency. So we've optimized the number of faults that we've introduced. We've optimized how we run things. We've pruned things down with a cone of influence analysis under the hood. We've farmed it out for you, which means that you get much faster turnaround time by running this within VC Formal than you could have by running it individually. And the native FTA is actually providing us with about a 5x speed up in the runtime. So bringing fault injection and Formal together in a way that makes it easier for the user to run, and it means that you can just set this going one weekend and come back and look at the results, makes it much easier for you to actually be able to sign off on Formal. And Formal sign-off is something which, because we're people involved in Formal, we really ask for a higher level of due diligence than necessarily other things would. With code coverage and even functional coverage in simulation, you're not getting the same level of rigorous testing that you get when you run Formal, when you go through these metrics, and then when you do the last stage of fault injection too. So in a summary of the different sign-off methodologies that we've looked at, we have cone of influence analysis, and that shouldn't be discounted. It's a worthwhile thing for you to run, but it's worthwhile to run for a first pass to analyze if you've got holes in your verification. Just figure out at the moment roughly what am I looking like. If I covered 50% of my logic, it's probably not worth trying to go through the sign-off motions. If I've covered all of my logic at this level, then I can actually start moving forward. Overconstraint analysis is always an important part to run. This isn't testing how good my assertions are, it's testing the results of them. So it checks the quality of the results, not the quality of the checks. And it's important to ensure that you aren't running in an overconstrained environment. Formal core is a robust formal analysis that is actually going to really analyze and check which pieces of logic have influenced the results of your checks. It will check which logic is being covered by the checks, but it doesn't check everything about that. It simply tells me, is this logic included in some check? It doesn't necessarily tell me everything. So fault injection can be used to ensure actual check quality by ensuring that my checks can catch bugs and checking the quality of these exhaustive checks that I've written. So thank you very much for listening, and I'll be happy to take any questions.
A big thank you for catching up our time as well. And, lost my mic. Okay. First talk. Just introduce yourself again.
Yeah, Sam Elliott, Imagination Technologies. So you mentioned that formal core was used as a sign-off criteria by some companies. So obviously it is a stronger metric than code of influence, but isn't it also dependent on the quality of the formal tools, in that if the formal engine were to be spuriously thinking it required something to prove it, but it didn't really, then that would be over-covered by this metric?
Absolutely. I mean, you can't guarantee anything, and repeated runs of a formal core may actually produce you slightly different results. It's not widely ranging, and you don't expect a huge difference in things, but depending on which engines run and depending on which engines report you the results, you're not guaranteed a minimal set of results, which is why, yes, it's a very worthwhile thing to do, and you're already getting a huge amount more than you would get from simulation metrics, but it's not foolproof.
Okay. Is that one? Oh, so it doesn't seem to be working. Okay, sorry, that one.
Hi, it's Karthik from ARM. Do you have any comparative numbers on performance, in terms of CPU side compute farm time for proof core versus fault injection?
We do have numbers. I don't have any of them with me here today. We can look at them offline. But yeah, so generally I would expect an FTA analysis to take a little bit longer than a formal core. So our kind of target goal is that a formal core analysis should never take you any longer than it took to run your proofs in the first place. And then beyond that, your FTA analysis depends on the size of the design, it depends on your assertions, but we do see a big speed up from having run this, for example, with certitude with a standalone formal tool. We see about a 5x speed up on that. So I do have some numbers that we can look at offline.
Okay.
I have another question. So the fault injection model, is it stuck at single bit faults, or?
So it's a little bit more complex than that. It's not just doing stuck at faults, but we'll do things like stuck at bit flips, logical operator changes, forcing of particular branches. All these kind of things are going to be instrumented by it, and it will depend on the fault model that you choose to use with it. But it's more complex than just stuck at. I mean, arithmetic logic isn't the right target for FPV in the first place. So we'll inject faults in there, and we'll change operators of things. If you've got a multiplier in there, we will change that operators. But as you well know, there's other tools that you would want to use for that in the first place.
Am I right in assuming you've got the same fault models that you use in simulation with certitude, presumably?
Yes.
Yeah, okay. And so one of the issues about the simulation, certitude simulation was, I think, as hinted before, was the performance, and that. Yeah. And then you have to sometimes run huge numbers of simulations. But I presume, is that resolved for formal?
This is something which we see running very well in formal. Okay. Because we reduce the number of checks that you actually need to run for any given fault, because we're doing this at the end of the tree, and because formal is exhaustive and can find you those failures a lot quicker, okay, it means that we're actually able to turn this around faster.
All right, okay. Yeah, I guess you're guaranteed to find the failure very, very quickly. Yes. The minimal number of states. Yeah. Right. Okay, I think we're done. So we're now going into our breakout sessions. So first of all, thank you very much, Iain. Thank you for the talk.